Okay. Everybody saw the project 2. So you start doing it. The only hurdle that you face for project 2 is you have to write a symbol table. So writing that symbol table might get a little bit tricky because now you have to deal with pointers. Initially you didn't have to deal with pointers for the first project. So whenever you have to deal with pointers, you get weird errors. So what I suggest is even before starting with the lexer or parser, just try to write a stack using linked lists. And so I have a small function that uses a linked list, implements a task stack, and try to test it out. And whether the stack actually works how you intend it to work. So that should be your first step. Now, if you go to the contents, assignments, I have some notes. These notes actually, we can go over this maybe tomorrow or the day after. We can go over this, but these notes actually explain how you have to write the code, right? So if you can understand whatever I have written, then you will know how to write the code. But if you cannot, we will discuss this. We will discuss this maybe tomorrow or the day after.
What is it under in content?
Just the assignment. Oh, you don't see assignment 2. You have assignment 2 recitation slides.
Oh, okay. Thanks.
Do you see it, or is it hidden?
Yeah, I see it.
Okay, that's good. So yeah, so it talks about you have to update the lexer. Updating the lexer is the easiest part because basically you already have the lexer. You have to strip it down. Okay, you have to strip it down, and you have to also add 2 more tokens, public and private. Those are the 2 tokens that you need to update. Then you have to write a recursive descent parser, the rules for each token or token combination. So basically, when you see the grammar, you won't find the recursive descent parser because that grammar is MD rules. So you follow the same rules of the recursive descent parser. Only when you come to the rules where you have a contradiction, right? So ambiguous grammar means what? You receive a token, it can go 3 ways. There are 3 different rules that you can follow. So what you have to do is, instead of taking just one route, you have to randomly choose one or arbitrarily choose one. You can choose always the first one by default. You go ahead. If you find that it does not follow the rule, you have to do unget card, not unget card, unget token. Don't do unget card because you won't get it. If you do unget token, then you can do it multiple times. You cannot do unget card multiple times. So you do unget token, come back to the point where you went into that rule, then select the other. And you do it 3 times. If there are 3 different rules, you do it 3 times. You will succeed once. If you don't succeed once, then you output syntax error. So now, while doing that, that is just the parser. So you haven't talked about this. We haven't talked about the scope yet. So once you have parsed it and you saw that there is no syntax error, go to each assignment. Now this you can do while you are parsing also. While you are parsing, whenever you parse an assignment, that is you receive that equal to sign. Whenever you parse an assignment, you add a variable inside that symbol. So whenever you see that okay A is equal to B, then you take A, add it to the symbol. If you can resolve the scope right then and there, then very well you resolve the scope and put the scope in there. If you cannot, just put question mark. Now how do you implement the linked list? So here I have all this parser algorithm and everything already written, right? So you can just follow this algorithm. This algorithm, so this one actually also specifies exactly where you have ambiguity. So this code has that ambiguity there. So if you see how I implement, here there are two unget tokens, right? So here there was an ambiguity. That's why I did two unget tokens. So once you do unget token, then you go into the next CLC. So this code already tells you how to write it for ambiguous grammars. So if you can understand it very well, or if you don't understand it, we will talk about it later. Then this is all the code, but most importantly, what most important is to write the linked list. So this describes the linked list that you should have for symbol table. So it says that in a symbol table you should have a structure which has an item. Now what is that item? We'll talk about later. And it has a next and previous point. So this symbol table item is another structure. It has the name of that variable, it has the scope of that variable, and it has an integer that says whether it is public or private variable. Right. So this is the type of the structure that you need to have, and this is the linked list that you need to make. So linked list of this type of structure. Right. So you do that, then this also. So you have to have add list, you have to have delete list, right? So this should give you plenty to think about. So keep these resources in mind. So this also tells you how you can implement the symbol table. So you have name, scope, permission, and then you have a doubly linked list basically. You have a doubly linked list, and it also gives you an example of how to do the scoping, and it also explains the algorithm of how to do scope. Right. So see if you can understand this. We'll discuss this tomorrow or Monday, whenever we get time. The TAs and the graders will discuss this in the recitation, but I'm not sure whether they'll be able to explain everything that is written here. I will explain them, but I will also explain you guys in one of the classes. Any questions on assignment homework, please?
Can you go back to the first PDF? And then, like, number 3, I guess. Step 3.
Slide?
Yeah.
Page number 3.
Bullet 3, I guess.
What?
Can you scroll up a little bit more? A little more.
What are you looking for?
Can you go to page 1, actually? Okay, yeah, 3 right there. So, is that what our symbol table should represent for that program right there on the far right hand side, where like the X's are and A, B, C?
I forgot actually. I have to read this and understand first. If you okay, what I can do is I can upload the recitation video where I explain this, but then I have to go and search which video. So I can do that. I can find out the recitation video that explains this and then upload that as well. So that will be an explanation for these slides. Any other questions? So let's restart. We are doing type systems, and we said that we want to do type compatibility. Type compatibility can be basically deals with equivalence, finding equivalence between types, whether two variables are of the same type or not. Right? So there are two different types of equivalence. One is name equivalence, another is structural equivalence. We say that what is name equivalence? Name equivalence means both the variables should have the same type name, right? And in case of anonymous types, there can be two ways. One way is that whenever a variable is declared as an anonymous type, the runtime execution engine or the compiler or the interpreter gives it a different type name. If it does that, then you cannot equate two anonymous types. But then there are certain interpreters and compilers that might give same name to anonymous types, same internal name to anonymous types. So if you are defining two variables in the same line, then these two variables might get two variables in the same line using anonymous types. Then these two variables can get the same internal name. In that case, you can have an assignment A equals B. That is type compatible. So we saw that was about name equivalence. Then we talked about structural equivalence, and we said that there are certain rules. There are certain rules for structural equivalence. First rule is that they have the same built-in types. That is the first rule. So built-in types means cm is an integer, int is an integer. If you have two variables, x is of type cm and y is of type int, you can do x equals y. Because cm is the same built-in type integer, int is the same built-in type integer. Right? So that is structural equivalence. That was the first rule. The second rule is pointers to structurally equivalent types. You can equate them. Right? If there are pointers to variables of the same structure, then you can equate them. So for example, if you have cm star x and int star x, then you can do x equals y. Right? That is possible because cm star is a pointer to a type that is equivalent to int. Right? They are structurally equivalent to int. So you can do int star y if you can do x equals y. So that is what it's explaining. Int star a, float star b, you cannot do a equals b. But it first was int star a and cm star b, you could have done that. Right? So that is structural equivalence. Then we say that how do we know that two structures are structurally equivalent? That's the third rule. So two structures are structurally equivalent if all the elements of the structures have the same type or structurally equivalent type. So if x1 and y1 are the first element, then w1 should be structurally equivalent to q1. Right? W2 should be structurally equivalent to q2 and so on. Yes.
So the order is important.
The order is important. So the order is important. So that's why this is correct. These are structurally equivalent. Although the names are different, variable names are different, but these two structs are equivalent structurally. But this one is not. The order is important. So because the first variable of struct A is of type int, the first variable of struct B is of type float. Mismatch. So that is not structurally equivalent. Then we started to argue about structural equivalence of arrays. We said that two arrays T1 and T2 are structurally equivalent if they have the same range, and small t1 and small t2 are structurally equivalent. So range has to be the same, and they have to be of same basic type or same or structurally equivalent types. Then we discussed about functions. So functions, if t1, t2 is a function, we declare functions like that. So it's a function of small t1 through tk, where small t1 to tk are the types of their arguments, and then you return the value small t. That is the type of the return value. So we say that all the arguments have to be structurally equivalent, all the return values should be structurally equivalent. In this case, we just have one return value. By the way, can you return multiple variables in a C function?
No.
No? Are you sure?
Can return a struct.
You cannot.
We can return a struct.
You can return a struct. You can return a pointer. If you return a pointer, you can intelligently use the memory to return to two or three separate variables. So as long as you can return a pointer, then you can return multiple variables. Right? So by intelligently using a pointer, you can do that. So it does not matter whether we are returning just one variable. It does not limit the definition of the function. Even if you are returning one type, you can use that type intelligently to return multiple variables. So the return value can be either a struct, as he is saying, or it can be a pointer. Right? So that is structural equivalence of functions. Now we come to the question is, how do we determine structural equivalence? There are those rules, those 5 rules, but we have to determine structural equivalence given an assignment, right? So it seems pretty easy because what you can do is you can start from rule 5 and break it down, right? And go to rule 4, then break it down, go to rule 3, break it down 2, and then finally when you have reached rule 1 says, okay, the type names should match. Rule 1 is basically name equivalence, because the basic types always have the same name, right? So if those names are not matching, then you say no. So that is good, but there is one big problem in that type of situation. So let's start from here. So the goal is to determine for every pair of types in the program if they are structurally equivalent. That is what is the goal. So it is simple because you can just start from the rule number 5 and then go to the base case, which is rule number 1. So once the base case is reached, you say, okay, there are the same basic types. If they are, then you say it's structurally equivalent. If they are not, you say no. Right? It seems pretty easy, but then there is a problem. How will you handle this following case? Right? So what is this? What is so unique about this case? So T1 is a structure where it has two. It has two variables. A is an integer and P is a pointer to T2. Right? T2 is another structure. So T2 is another structure where A is an integer, but P, the next variable, is a pointer to T1. Right? So how will you go about arguing about the structural equivalence of T1 and T2? So you apply rule 5. What is rule 4 first? Sorry, no, rule 3. Right? Structure equivalence of structures. So rule 3 you apply. So rule 3 says that okay, all the variables have to have the structurally equivalent types. So the first variable is fine because the int structurally equivalent. Second variable, what happens? So it's a pointer to T2 and pointer to T1. So you use the rule 2 because rule 2 says how to argue about structural equivalence of pointers. That is what rule 2 says. So pointer says that if it is a pointer to the same basic type, then they are structurally equivalent. Now you say that okay, that the second variable of T1 is a pointer to T2, and the second variable of T2 is a pointer to T1. So if I can prove that T1 and T2 are structurally equivalent, then T1 and T2 are structurally equivalent. So it becomes recursive. So now again you try to do, okay, let's see whether T1 and T2 are structurally equivalent or not. Again you check the first variable, you say yes, it's structurally equivalent. But you go and check the second variable, you again see that okay, it's a pointer, so apply rule 2. Again you come back to the question whether T1 and T2 are structurally equivalent. This can go on forever, right? So we'll never end up saying whether T1 and T2 are structurally equivalent or not. How will you break this cycle? So that is the problem. The problem is you can go on. Applying the rule states that T1 is structurally equivalent to T2 if and only if pointer to T1 is structurally equivalent to pointer to T2. And if you apply rule 2, it says which is true if and only if T1 is structurally equivalent to T2. So you switch. You keep on switching, no end. So how to end it? How you'll end it is that you'll assume that, let's say T1 and T2 are structurally equivalent. Assume. If while evaluating other types you see that there is a contradiction, then you say that no, T1 and T2 are not. So if there was no contradiction, you assume that T1 and T2 are structurally equivalent. Okay. So that is the basic rule. So again, reiterating, to break those cases where you are going back and forth in an infinite loop, to break such cases, what you first assume is that, let's assume that T1 and T2 are structurally equivalent, because there are no rule that contradicts it. If there is some rule, some example that contradicts it, then you say that no, we were wrong in assuming that. Right? So that's how you break such problems. So now what we'll do is we'll try to devise an algorithm. We'll try to devise an algorithm to check type compatibility. Right? So what we'll do is we'll create an n cross n table where n is the number of types in the program, and each entry in the table is true if the types are structurally equivalent. So you have in a code you might have defined different types, right? So whatever types you have defined, you put it in an n cross n table. So types. Then you'll see whether these two are equivalent or not. If they're equivalent, you'll say that okay, that is true, that entry in the table is true. If not, then false. So if you consider the diagonals of the table, will all of them be true or false? True. They will be true, because T1 is structurally equivalent to T1, right? So the diagonals should be true. Right?
One diagonal.
Yes, just one diagonal. Yes. One diagonal. So to support that cyclical definitions that we have, what we did for cyclical definitions, we said that if there is no rule that contradicts, we'll assume that they are structurally equivalent. So in order to support that, what we first do is create the table and put all the entries to true first. So we assume that the types are structurally equivalent until we have proof otherwise. So innocent until proven guilty. We'll use that same rule. So what we do is set the n cross n table to have each entry as true. Then while table has not changed, we check the entry ij in the table. If ti and tj are not structurally equivalent, then set the entry ij to false. Very simple. So now let's do this. So let's say we have these three types of definitions, three types of type definitions. So this is an example. So what is T1? T1 has the first variable is int, the second variable is pointer to T2, and T2 is a structure which has the first variable as int and the second variable is a pointer to T3, whereas T3 is a structure where first variable is float, second variable is pointer to T1. Let's see what happens when we do a type compatibility test. So what we do is we create that n cross n table. So T1, T2, T3, T1, T2, T3. Everything we initialize to true, right? Now let's evaluate this. This will be true because T1, T1, T1. They are the same structural equivalent type. Let's say T1 and T2. Can we evaluate whether these are true or not? So if you first see, if you want to do T1 and T2, these are two structures. So let's apply the rule number 3, structure equivalence of structures. So we see that the first variable, they are structurally equivalent because both are of the basic type int. So we apply the rule 1 and we say that A and C are structurally equivalent. Then we come to the second one. We say that okay, P is a pointer to T2 and Q is a pointer to T3. So we apply rule 2. So why, when can pointer to T2 be structurally equivalent to pointer to T3? If T2 is structurally equivalent to T3. So if that is the case, that's what happens. So now let's check whether T2 is structurally equivalent to T3 or not. If you want to check that, you just look up the table. You say that okay, T2 T3 means I have to check this entry. T2 T3, which means this entry. Right? I have to check this entry. At this time, this entry is true. Right? So we come to the conclusion that P and Q, the second variables, are also structurally equivalent. We don't have anything to disprove this. Any rule yet to disprove this. Right? So we assume that T1 and T2, this remains true. Do you understand this? Anybody has doubts regarding this one?
I'm gonna go back and check it again.
Yes, we will. We will continue because we haven't checked all the entries yet. We'll check all the entries and see if anything changed. If anything changed, we'll do it again. Right. So T1, T2 remains true. Is that clear? Anybody has doubts regarding this? No. Doubts? No. So let's check the next one. Let's check T1, T3. So T1, T3 says, okay, we have this structure, so apply rule number 3. So it says that the first element, it has to be structurally equivalent. Are they structurally equivalent? No. So immediately T1, T3 is false. Right? So T1, T3, we change it to false. So if T1, T3 is false, T3, T1 will also be false. Right? So it's commutative. So if it's commutative, we will just make those two terms same. So basically, this array should be a upper half array, right? Upper diagonal array, or lower diagonal, whatever you want you choose. So you can just remove the lower diagonal. So now we had false. Now what do we need to check? We already checked T1, T2, right? We already checked T1, T1, we already checked T1, T2. So if we check T1, T2, then T2, T1 is also checked, right? We don't need to check T2, T2. So what we need to check is T2, T3. Are they structurally equivalent or not? So let's check this one. So T2 and T3. So if we again apply rule 3. We see that the first variable is not structurally equivalent. Yes.
If we know that T1 and T2 are structurally equivalent, then can we assume that T2 and T3 are not equivalent since T1 and T3 are not equivalent?
There is no transitive rule.
Okay.
So maybe conceptually yes, you are right. But since there are no transitive rules, we cannot do that as of yet. Right. So let's check T2, T3. So we say that okay, the first variable is not, so this is false. This has to be false, right? And if that is false, then we make this false as well. Now the array has changed, right? The n cross n array has changed. We have to check again. We have to check again. So let's check again. T1, T1 we don't need to. T1, T2 we need to, right? So we see that okay, a int, c int is the same. The second one, pointer to T2, pointer to T3. So we should check T2, T3. Now we see T2, T3 is false. So we change this to false, right? If we change this to false, this also changes to false. Now it has changed again. So we have to do it again, right? So we do it again. Basically nothing changes anymore, right? Because T1 has to be true, T2 has to be true, T3 has to be true, and others are all false. So now nothing changes. We are done. So that is how you check structural equivalence. Any doubts?
Is this polynomial time?
What do you think? Do you think it's polynomial time? What is the order?
N squared?
Yeah, n square. Order n square. So this is a polynomial time algorithm. Why is it important to you? If it's polynomial.
Compile time.
Runtime. Yes, compile time will also decrease. So yes, this is a polynomial time. We actually don't discuss these things in this class. If you take 310, how many of you have taken 310? I think I have asked this many times.
It's pretty right.
No, there is a period. So 310 you have to take. So in that course they might have discussed all these things, like order and all those. So let's now talk about a different topic. But before we go into a different topic, do you have any questions with respect to type equivalence? So we have discussed type equivalence. We didn't discuss type inference and type conversion. We haven't discussed it yet. So we'll discuss it next. Any questions so far? Now we come to a very important concept. So the concept is that when we discuss the type equivalence and structure equivalence, name equivalence, what did we do? We said that at the beginning of the program you have to declare all the variables, all the types, right? C does that. C requires you to do all those things. And you have to, at the initial, you have to declare all the types, you have to declare all the variables. But there are certain programming languages which do not need you to declare the variables, to declare the types. In those programming languages, there has to be some way to understand what type is a particular variable. What type does it resolve to? Right? So we now are going towards type inference systems. How can you infer a type given a code? And how can you infer that maybe a particular assignment is wrong, even if you haven't declared variables? Right? So for example, in MATLAB or in Python, you don't need to declare variables. In that case, how do you understand that a particular variable is a string or a character, or can you even apply a particular equation that you have used in a program? So we are coming to that. So what we did so far is that we have to declare a variable, so we can declare it like this: array 0 to 5 of int a, then int I, we declare the index, and then we can write a I equals 1. Right? That we can write. Now what if we have this? If we declare a string equals I, can we do this? Is it possible to do this? You cannot. You cannot have string as an index. Index of an array has to be an integer. Right? Can we do this? Are you sure?
Because it's declared as an integer, right? So
You cannot really do this, but if instead of testing I have just T,
Yeah.
then you can have a character, you cannot have a string. So character can be converted to integers. There is a type conversion rule, but you cannot convert strings. Right? So this you cannot do. Now we come to the concept of parameterized types. So some languages allow programmers to declare parameterized types. Can you give me an example of parameterized types? Yes.
Java generics,
Yes, Java generics, or much simpler, you can take a C++ example,
templates.
templates, functions, you can override functions, right? They can have different input arguments. So those are parameterized types, right? So basically instead of being specific to a given type, the specific type is given as a parameter. So this type is kind of like an abstract data type. Right? Abstract data type means you can cast it to integer, character, or what you want, but that data type is parameterized. Right? So generics, as he said, generics in Java, templates in C++, those are examples of parameterized types. So let's see an example here. This is a Java code, right? So Java code is doing what? There is a public class called chooser, and there is inside the chooser there is a function called choose, right? This function takes two items, first and second, and their types are not declared. There's some generic types T, right? And that type is parameterized. It can be variable. So what does that choose do? It takes the first and the second element. It randomly chooses the first or the second one. It just randomly does. So when you call choose, it will return either the first parameter or the second parameter. You don't know which one. So if you write that main function, so x is 100, y is 999. If you do chooser.choose x comma y, it will return you either 100 or 999. You don't know randomly, but it returns you an int. So it tries to understand, based on the types of x and y, it tries to understand what should be the return type. It understands that the return type should be an int, and it returns int. If you have string a equals foo, string b equals bar, and do chooser.choose a comma b, it will return a string. It will not return an integer, right? So based on the input arguments, type of the input arguments, it will return you the appropriate type. So how does it know? How does it know that the return value has to be string? So there must be some rules. You must have inferred the type in some way or the other. You must have inferred the type. So we have to define those rules. So before we go to those rules, there are certain concepts that we need to understand. The concepts of polymorphism. Anybody familiar with the concept of polymorphism? What is it?
You can have the same name for different operations.
Yes. For different functions, for different classes, you can have the same name. So let's see. This concept is explicit polymorphism, right? So what happened in the previous example? In the previous example, the programmer declared the parameterized types explicitly. So it said, okay, there is this first type T and there is the second type T, right? So only these parameters, the types are variable. So the programmer has to explicitly say that the first and the second argument has variable types. So that is explicit polymorphism. You don't have to worry about object-oriented context now. So the compiler and interpreter will allow a function to be called with different types. So that is what happened in the previous example, right? Now, slightly different concept is implicit polymorphism. So the programmer does not need to specify the type parameters explicitly. So this is we'll see an example, but this is a property of dynamic languages. So what happens is that the type checker will statically attempt to assign the most general type. The most general type to every construct in the program. So let's take an example. So if you have fun foo x equals x, this is what this is MATLAB code, right? Here you don't specify what is x, what is the type of x. So you didn't explicitly specify that tx equals tx, right? So you don't say that okay, that x and that x has to have the same type. You don't say. But if you run this code and you say foo10, what will be the return? What will be the return type? You haven't said that the return type is t. In the previous example, explicit polymorphism, you said that okay, the first element has to be of type t, the second element also has to be of type t, and the return type also has to be of type t. Yes. This could have been t1, t2, t3. This could have been that. But you explicitly said that all these should have the same type. But in here, you are not explicitly stating. You are just saying foo x equals x. You don't say what is the type of x as an input argument. You don't say what is the return type of foo. You don't say. But if you call the function as foo10, if you give the argument 10, what will be the return value of that function? In MATLAB, if you do yes, 10. It will output 10, right? Because it is giving foo x equals x. This is functional programming language, where every line of code is like a function. We'll talk about that later. Functional programming language when we talk about lambda calculus. That's probably the last topic we'll talk about, and it will get very weird when we talk about lambda calculus. So fun foo x equals x. So how do you know what is the return type in this case? So you have to have some rules. This program should have to have some rules of inferring types. So one of the rule is function. So you can write this foo x equals x as function of t. So just assume that x is of type t. T is a general type, right? X is of type t. Assume. Now, since this function returns the value of x and x is of type t, the function's return type should be t. Right? That's what you are. It cannot be anything other than t because we don't have any other information. If we had any other information about this function, then we might choose a different type. But as of now, the most generic type that we can give to the return of foo is t. Which means we are saying that it has the same type as its input argument. So we say that okay, function of this, the foo has a type function of t and it returns t, and this we can denote it like this. So within parentheses, capital T, then right arrow, capital T. So right arrow is the return type. Right arrow is the you use to give the return type. So we can represent it as this. Now if we have these two, function foo x equals x, and then we have another function bar y equals foo y. We know the type of foo x. Type of foo x is what? Is function of t returns t. From the definition here of bar, can we identify what is the type of bar? What is the most generic type that we can give to bar? First of all, in order to give a generic type to bar, we need to identify what is the type of its input argument. So what is the type of y? What type can we give to y? Remember, you have the information that foo x equals x. Foo's type is function of capital T and it returns capital T. So if you know that, what should be the type of y?
T.
Type of y should be T. Because we know that the type of foo is function of T returns T. So whatever is the input argument of foo has to have a type T. Now we have used y as input argument of foo. So y has to have the type T. Right? So if y has to have the type T, then what is the type of bar?
Same. T.
So input argument of bar also is type T because bar uses y as input argument. Right? So input argument of bar has type T. What is the return type of bar? So if you follow the function, what does bar return? Foo y returns y. Foo y will return y. So if foo y returns y, what does bar y return?
Y.
It also returns y. So the return type of bar is what? What is the return type of bar? T. Right? So by just writing these functions, we can argue that the return type of bar, or foo has this type, and the return type of bar is same as the, or the type of bar is same as type of foo. We didn't declare any types. We didn't declare type of x, we didn't declare type of foo, we didn't declare type of y, as well as bar. But by writing these two lines of code, we can understand, we can extract type of foo as well as type of bar. We can give some most generic types to foo and bar. Right? So this is implicit polymorphism. So we don't explicitly identify the types of the variables and functions, but by just writing the code, by just analyzing the code, you can extract, you can kind of understand what is the type of foo and what is the type of bar. You can give them the most generic types. That is possible. So do you understand how we got the types of foo and types of bar? Do you have any problems? Anybody has any problems understanding this? Implicit polymorphism. Okay. Let's take another example. So there's this function. These are all functional programming languages. Right? MATLAB is an example. So if you have this, max x comma y equals, if x is less than y, then y is x. So this type of function definition is kind of weird, right? How can you have equals and then you have if? So this is typically how functional programming languages are expressed. So what is the rule? The rule is max fun max xy is equal to a certain value, right? So what will be that value? Whatever is the expression there, you evaluate it, whatever it returns, that is the output of max, right? So now max xy is an expression. So evaluate that expression. What is that expression? That expression is if x is less than y, then you give y, if else you give x. So if I say max 2 comma 3, what should be the output? 2. If I give max a comma b, still a character, what will be the output? Max small a comma small b. should be B, because you can, if that, it depends upon that comparator, x less than y. You can convert into ASCII, so A will be always less than B, so it will output B, right? Can you also do max 2 comma A?
Doesn't
It depends. It depends upon the interpreter or compiler. If there is a less than function that can compare a character and an integer, then you can. You can take the ASCII value of that character and compare it with the integer. That you can do. But then what will be the return type?
integer.
Why?
Because characters are converted to integers before they're converted. Usually.
Yes, I mean you can do that. But ideally, if you want the string as an output, then this function can either return integer or character. That gives a contradiction. That is ambiguous. So we have to define rules for those kind of things. So we have to define rules. So now intuitively, what should be the type of max? If you should not have, if you don't want to have that kind of a mix, if you don't want to have a contradiction in the return type, and if you assume that the less than operator always operates on the same type, you cannot have like an integer and a character and then compare, right? If you don't have that, then what should be the type of max? Yes?
Int.
No, give a generic type.
Keyword choose one.
Now, can you compare a string with a string using the less than operator?
Yes.
Yes, you can. In C, you cannot.
Oh, that's
In some language, you might be able to. So in C, if you think of this, then you can have a type like this: function of int comma int, and it returns an int. Right? You can resolve it like this. So you can express it using this int comma int, like with parentheses, and then right arrow int. That is the way we will express it. Now this is a more generic version of the function max. Instead of having less than, we have CMP. CMP is some comparison. We can do some comparison. And that comparison can be a function. It can be a function itself. Right? It can be either the less than operator, or it can be a string compare. It can be anything. So now how do you declare the type of max? So compare, remember, compare will take two same types of variables. It cannot again compare two different types of variables. It will take two same types of variables and give it 1 or 0 as output. If you think of compare, if it's less than, then it takes two integers, it says which 1 or 0. Right? X is less than y. If x is less than y, then it gives out 1, if not 0. If you take that string comparison, then it says that maybe it can compare lengthwise. Which one is the longer string? Right? So x less than y, if x is shorter than y, then it will return 1. If x is longer, it will return 0. So now first you have to argue about what is the type of CMP. What generic type can you give to CMP? What is the most generic type?
Wouldn't it have to be T?
Yes, x and y can be T, and they have to be the same type because CMP does not take two different types. It can only compare between same type. So CMP is a function of T comma T. Right? The two arguments have to be of same type in CMP. So T comma T is a function of T comma T. What is the return type? Is it return type T?
Oh, it's
Because you are
also-
using it
it's
in if.
It can be an integer.
No, not integer. It cannot be an integer. Yes?
For true or false.
Yes, it has to be Boolean. Either true or false.
So what's the, because we have three situations, either x is larger, y is larger, or they're equal. So
Yeah, if they're equal, you just choose between 1 or 0 randomly. Right. So CMP has to return a Boolean. So now if that is the case, if CMP returns a Boolean, what should be the type of max? Max will be this. So it is a function of, it has 3 arguments. The first argument is another function. And what is the type of that argument? It's function of t comma t, and it returns Boolean. Then the second argument has to be of type t. The third argument has to be of the same type t. And the max returns the type t. Is there any confusion between with the type of max? Do you understand why type of max is that? Again, it has 3 arguments. First argument is the function. That function takes 2 of the same type, returns a Boolean, right? And since CMP takes x and y as arguments, and they have to be of the same type, so x and y in max will also have to be of the same type, right? So that's why you have comma t. The second and third argument are of the same type t. Now since max returns either x or y and both have the same type t, the most generic type we can give to the return value of max is t. And we do not have any other rule that says you can give a different type, right? So that's why the type of max is that. Any confusion in this? So how you can write this? We will follow this symbol, this rule to write the type. So within parentheses, we write the input arguments. The first input argument is the function itself, so we'll have the same format. Within parentheses, input argument of that function t comma t, then right arrow bool, and then the second and third parameters of the max function, and then right arrow t. Right. So that is the format that we use. So we can call it like this: max less than 10, 200. We can call it like this, and we'll get the value. What will we get? 200. Then we can also use this strcmp, right? Foo bar. We can also use the max as this. So that is another example of implicit polymorphism. So you have the same function max, and you're using it to pass integers, or you're using it to pass strings. Now how do we know that which function you are calling? Is it the string function or is it the integer function? That is the task of the type inference system. We'll talk about type inference system in a bit. Now let's see another type of polymorphism. How about this? Foo A, B, C equals C, then within parentheses A, then index B. Right? So here A index B, that means what? So what is B? What should be the type of B? What is the most generic type that you can give to B? It has to be an int. Index cannot be a string, index cannot be a float. Right? Array index has to be an integer. So the most generic type that you can give to B is an int. You have to give B as an int. So if B is an int, what is A? Yes? Of? So what do you give the most generic type? It's an array of T. So but if you want to give the type to A, then you have to give a range. What range do you give? At this point, you don't know the range. Right? At this point, you don't know the range. So you cannot give any range to A as of yet. So what you can only say is that small a is an array of type T, right? The most generic type T. So B is an integer, A is an array of type T. What is C? What is the most generic type that you can give to C?
It's a function
Yes,
that takes an array.
yes. It's a function that takes an array of type T as input. What is the return type?
T.
Why?
Because that's whatever A and B returns.
But that is the input. The input may not be the same type as the output.
We can say R.
So then T2.
T2, right? The most generic type of return type of C can be T2. Here I have given U. So now who has this type? It's a function of some things. So it's what are those things? The first argument is an array of T. The second argument has to be an int because B is the index. The third argument is function of T and returns U. And what should be the return type of foo? It should be whatever C returns because that is the function, that is the expression, right? So again, you see, even without explicitly declaring that B is an int, we found out that B has to be an int from the code. From the program, we can find out, we can infer that B has to an int because it's an index to an array, right? So just by looking at the code, we can determine what is the type. So that is implicit polymorphism. That is another example of implicit polymorphism. So how do we again represent this using our technique or format? Within parentheses, we say array of T comma int, and then again within parentheses we say T right arrow U, and then finally right arrow U. Right. So this format, it's pretty easy to understand, but you have to keep this in mind. How about this? What is the type of foo? So we have a function foo a ec. We initially assign a equals 10, and then we do that a parenthesis b c. So by looking at this, what should be the type of C? C has to be in because C is an index to the array. What is the type of B? Array of T. What is the type of A? Why?
Because it's a function that takes an array of T.
So if she says error, he says it should be a function.
What does it mean to apply a parenthesis to a number? I think the language should define that.
So A we have declared it as int, A equals 10. When we run the first line, we know that A is an int. Then when we run the second line, we are trying to use A as a function. So it's a contradiction. A sometimes is an int, sometimes a function. This cannot work. So this is a type error. Okay. So even without declaring, we know what is type error. We don't have to declare the A as an int. By just writing the code, we can also extract or kind of understand or make out that this is a type error. So again, that is another example of implicit declaration, or implicit polymorphism. So now here what we see is that even if you do not explicitly declare types of variables, we can follow certain rules. We can look at the code, we can follow certain rules and we can identify types. Not only we can identify abstract types, we can also identify basic types. We can say what is an int, right? What is a function? We can identify basic types. Not only we can identify basic types and abstract types, we can also identify type errors, right? By just looking at the code. We don't need explicit declaration. So how do we do that? What rules do we follow? The rules that we follow is embedded in what is called a Hindley-Milner type checking algorithm. So now we will talk about this Hindley-Milner type checking algorithm or HM type checking algorithm. So this is not really a type checking, rather this is a type inference engine. So it does type inference and then checks. So it has to do type inference automatically. So HM type checking is a general type inference approach. It infers types of constructs that are not explicitly declared. It leverages the constraints on the of the various constructs, and then it applies these constraints together with the type unification to find the most general type for each construct. So now there are two concepts. One concept is that there are certain constraints on types. Constraints means if you have an array, the index should be int. There is one constraint. We'll see what other constraints are there. And then it has another concept called type unification. So you have to unify types. You have to say that type T1 is same as type T2. So how do you do unification? The unification is basically if you do not see that there is an error. If you make type T1 equals T2 and you don't see that there is a contradiction, then you say that type T1 and T2 are the same. So you first unify and see, okay, if it contradicts, then you won't unify. That's how you do unification. So we'll see some examples and also some rules. So the full HM type checking is used in Haskell and those type of functional programming languages, basically. Now this is not used in C. So we'll see what are the different ways we can apply HM type checking. So first of all, we need to understand constraints, because we see that there are two things: constraints and type unification. So let's see how to understand what are the different constraints that are there. So first of all, we have to have constant integers. So 0, 1, these two, all these values have to have the type int. Whenever we have certain values like this, we have to have the type int. We have to have real numbers also. So 0.1, 2.2, whenever we have that, we have to have type real. Then booleans, true or false, will have to have the type boolean. Your third project, I think, is related to this type checking. Then strings, foo, bar will have to have this type string. Then we have certain constraints on operators. So we define something called relational operators, AOPB, right? So if we have AOPB, then the OP, so it will be represented as like this. So OP's return type will be T1, let's assume. And let's assume A has type T2, and let's assume B has type T3. So three things: OP is return value, then OP is argument. So OP can be less than equal to, greater than equal to, not equal to, or double equal, right? What are the constraints? Constraints is that T1 has to be Boolean. Whenever we have this kind of an operation, AOPB, where OP can be less than equal to, greater than equal to, and so on, the return type of OP has to be Boolean. That is the constraint. Then another constraint is T2 has to be equal to T3. So we don't have that T2 is integer or character. We don't have that constraint. The only constraint we have is that T2 has to be equal to T3. We don't care about the result. What is the result? We don't care. We only care about types here. So the when we have A, OP, B, then OP's type has to be Boolean, and the arguments of OP, like A and B, has to have the same type. T2 equals T3. This is when OP is a relational operator. Now what happens when OP is an arithmetic operator? So plus, minus, divide, multiply, those things. So again we represent them as trees. So OP is the root and A and B are the left and right child. And let's say initially we don't have any constraints on the type. So return type of OP can be T1, that of A can be T2, and that of B can be T3. Now we define constraints. So if OP is plus, minus, star, divide, then the constraints are T1 has to be equal to T2 has to be equal to T3. Right? So T1, T2, T3 has to be equal type, and what is the return type of OP? Is the same as T2 and T3. So T1 equals T2 equals T3. That's the constraint. Then we have array operators. If we have this A, then index B, then the constraints are okay. So we represent it in this way. We have a tree representation for operators as well. So for array operator, we have the root node as that open and close square brackets, right? And then the right node is A and the left node is B. So note that these tree representations, these have to maintain the order, right? So you cannot have B and A switched, then that will mean different. You have to A, then you have to first have the root node as the open and close square brackets, and then A as the left node, B as the right node. You have to have this, you have to follow this formula, right? So then what are the constraints? Constraints is the type T2 should be an array of T1. That is how we define it. So T2 is basically an array of T1 and T3 has to be int. That is how we define it. So A's type is array of T1 and B's type is int. Then we go on to defining functions. So how do we write the how do we draw the tree for the function? So in this case, if we have foo x1, x2, x3, xk, then we define a new root node. This root node is called apply. Right? So this root node is called apply. The rightmost or the leftmost node is foo. Then we have the arguments as the other children. So T1, x1, x2, xk. So the type of apply is R. Right? We will say that is the R. So that means that is the return type. Right? The type of the root node. The type of the function is F. And the type of x1, x2, xk are T1, T2, so on up to Tk. That is how we are defining. There is no reason why we are doing this. But that is one way of defining the function type. So now what are the constraints? F has to be equal to this open and close parenthesis T1, T2 up to Tk, then right arrow R. That is the only constraint that we have for functions. So this is function application, which means when you actually evaluate that function. So in a code, if you have foo 1, 2, then this is how you will represent it. As opposed to function definition, you can also have definitions of functions, right? So that is one function definition we saw. So we have a fun keyword, then foo, then the input arguments, then equal to some expression, right? If x is less than y, then x is y. That was the expression that we used. So if we have a function definition, then function definition has a different way of representation than function application. Right? Application means you actually evaluate the function. Definition means you are just writing what is inside that function. Right? So definition is different from application. How you define? is that you have a node called fun, and then you have another node which looks like this. And this does not really mean anything, but it looks like this. So what does it mean by looking like this? You have to have this foo, the name of the function, then all the arguments, right? Then you give the type f to foo and t1, t2, tk to those arguments. That is how you are representing the function. Why you are doing it? No reason. Right? Let's assume that we are doing it like this. We will see how it is useful later. And then the right child will be this expression e, right? So expression and its type is e. That is how you are representing. Now what are the constraints? The constraints is foo has to be this, or f has to be this. Open and close parenthesis, t1, t2 up to tk, and it has to return whatever is the type of expression. Whatever is the return type of expression, it has to return that. That is the constraint. So that is how we do function definition. Then we look into how we express the if condition. So we have this if expression. So how do we represent that? So in order to represent that visually, what we do is we have a root node called if and give it type t4, generic type. Then we have the condition as its leftmost child. This type is t1. Then we have expression 1 as one child and expression 2 as another child. Right? So t2 and t3, we give the types to expression 1 and expression 2. Now what are the constraints? The constraint is t1, that is our condition, has to be Boolean. t1 has to be Boolean, and t2 has to be equal to t3, has to be equal to t4. So these are the constraints. Right. Now this was a lot to take because we have a lot of things. So what we'll do is we'll stop here. Because the next thing we have to discuss is type unification. How do you unify type? But we'll stop here, and when we start tomorrow, we'll again reiterate this condition, constraints, and how we do it. And then we'll go to type unification and type.
I don't know if that'll make any I think I got it.
In the case that we had 10 of